Okay, so we continue our session of this afternoon, and we have a talk now from Alejandro Rivero Santamaria, who is going from Université de Lille, who is going to talk about high-dimensional atomistic neural network potentials to study gas-surface interactions. So Alejandro, you can start your talk.
So thank you very much for the presentation, and thank you very much to the organizer for the invitation and for the opportunity to make this talk. My name is Alejandro Rivero Santamaria. I am working the PCMT team in the FLAM laboratory at the University of Lille. And today the idea is to talk about the high-dimensional atomistic neural network to study gas surface interaction. And I will use a study case to illustrate how we can use this kind of potential energy surface for the study of high-dimensional system. So here, the outline of my presentation. Sorry, I will begin with the introduction of my presentation. The first part was dedicated to speak why is important the study of the gas surface interaction. And I will speak also what are the main mechanisms present in gas surface interaction. I also will speak about the molecular dynamic methods that are most used to study this kind of reaction. So in the second part of my talk, I will present the workflow to obtain the neural network PES, and I will present some fundamental about the atomistic neural network. In the third part of my talk, I will speak about the study case, that is the scattering of the O2 molecules from graphite, and I will speak how to prepare a neural network PES. So I will present the configuration sampling, the neural network training, the neural network Pes validation, and I will show some results about the molecular dynamics using this neural network Pes. I will finish, of course, with the conclusion of this work. So why is important to study the gas surface interaction, where the gas surface interaction are important because there are present in several applications in our life. For example, for understand the heterogeneous catalysis that is very important for the industrial processes, for understand the surface oxidation by the interaction of O2 molecules with different kind of surface, the material degradation that they happen when the spaceship go out in the atmosphere and have some interaction with the gas that are present in the atmosphere. Also, for example, to improve the mechanism for the hydrogen storage, and also, for example, for the detection of contaminant gas in the atmosphere. So here I divide the main mechanism that could be present in gas surface interaction. For example, you have the molecular absorption. You have different kind of mechanisms for the molecular absorption. You have the dissociative molecular absorption, the chemisorption, and the abstraction. You have also the molecular desorption. You can have, for example, the Lambda high wall mechanism, the Lee-Reidan mechanism, and the hot atom mechanism. And you have also the molecular scattering, where you can find, for example, elastic scattering, rotational inelastic scattering, vibrational inelastic scattering, and diffraction. Today, I will concentrate, or the study case that I will present to you is concentrate to the molecular scattering, and we will see that we have a mix between all these mechanisms. As you can see here, all these mechanisms are complex. There are in this system we have many atoms, so there are a high-dimensional system, and the study by the theoretical way of this system is very complex. So what are the molecular dynamics methods that are more used to study the molecular dynamic, to make molecular dynamics over this kind of gas surface system? Well, the well-known, we can use the potential energy surface based on analytical expression like Lennard Young, London Erin Polai, Sato, for example, that we know that are computationally efficient, very computationally efficient, but a lack of flexibility is present because we cannot take into account the system particularities and all the degrees of freedom that are present in this kind of complex system. Also, we can use the potential analysis surface that are based on interpolation of density functional theory. For example, the corrugation method that is well known, and some kind of neural network also that were used to study this kind of system. In general, what we do here is obtain a grid of DFT points, make interpolation, and after, with this interpolation and this analytical potential analysis surface, we perform the molecular dynamic calculation. But it's well known that we have here a limitation in the description of the surface corrugation, because normally we obtain a 6D PES that are able to study some feature of the system, but are limited. The third method that I want to present is the initial molecular dynamics. As you know, this is based on DFT on the fly, and all the degrees of freedom I take into account in this calculation. But we know that it's computationally demanding, because we can perform few trajectories, and then we have a low statistic of our processes. So the combination between this ab initio molecular dynamics and the high dimension atomistic neural potential could be the best option to study this complex system, and I will try to show you during this presentation why. So I will present briefly the methodology that we need to follow to obtain a neural network PES. So this is the workflow that you must to follow to obtain a neural network PES. The first step for sure is have the data, that is the bottleneck in the application of machine learning methods. You need to have a data. So for this data, you can obtain the data using an electronic structure calculation. In this case, in my work that I'm pressing here, I use a IMD calculation, and you can use, for example, a software like BAS, maybe Quantum Espresso, CP2K. But in any case, you need the data to have a neural network. This is sure. The second step, after you have the data, you make your calculation, is the data preparation. So you need to be able to extract the data from the calculation that you made. That means that you need to have the configuration and the corresponding energy and force of each atom for the selection that you make. So you need to classify and select the more representative data of the system. You cannot do the training process of the neural network with all the data. So you need to make a classification of your data. And this is the second step. The third step for sure is the neural network, the obtaination of the neural network based PES. For that, you need to select the architecture of the neural network that you will use, the symmetry function that you will use, and for sure after that, you are able to do the training process. For the training process, you can use the software of your relation. I put here some open source code that you can find on internet to do this kind of calculation. ANet, AMP that is based in Python, Prophet that is Prophet, and ANet that is based in Fortran. So after to make the training process, you need to pass to the validation step, that is the PES validation step. So you need to check the results, but now you need to use the unknown configuration to be sure that your neural network is right in the prediction of the property of the system. And you must to perform some molecular dynamics tests, and normally also you need to come back to the first step, because you need to add some configuration and make retraining and do the retraining of your neural networks. At the end, when you are ready, you pass for all these steps, you are ready to use your neural network PES to perform your molecular dynamics calculation. So for that, you need some homemade code, or you can use some commercial code that can be linked with the neural network that you obtain using one of these software. Okay, So here I presented in brief what is the fundamental of the atomistic and neural network. We begin with the famous expression of Beller and Parinello that is the base of the atomistic neural network. So the total energy of a system like that, with many atoms of different species, for example, can be expressed like the sum in elements of the different species and the sum of the individual atomic energy. So each atom is described in local environment that is defined by a cutoff radius. So you describe each atom of the system with this local environment, and this local environment is described by the so-called symmetry function. Here I present the symmetry function of Beller that are the most used now. This is a kind of function that must be invariant to the rotation, translational, and permutation. So this is important in this symmetry function. This is a kind of Gaussian function which you multiply for a cutoff function for obtain this environment that is represented here in red. And you go with this description of your environment to the neural network architecture. So we are agreed that here we have the Cartesian coordinates. We express the Cartesian coordinates in the way of the symmetry function. So here is what we call in the machine learning language the fingerprint of your system, and is the first layer, is the input layer, in fact. And after you come with the neural network that you have individual neural network for each species of the atoms, and the role or the objective of use this neural network is to obtain the weights to multiply this symmetry function in order to obtain individual energy that after the summation gives you a total energy that must to be very, very close to the ab initio energy, to the DFT energy. So this is the fit process, and the neural network is used to fit the weights in order to obtain the good total energy that must to be very, very close to the DFT energy. So this is the resume of how is work the neural network. If you want to go deeper, you can review this amazing review that was made by Beller in 2021 and have a lot of detail of this method. So now I will pass to present the study case. This is a work that we made in 2021, and we obtained a high-dimensional atomistic neural network to study the alignment result O2 scattering from highly oriented pyrrolite graphite. My idea here is to show in the practical case how we made the neural network PES, and what are the validation steps that we made, how we choose the configuration, and what are the results that we obtain after all this process. So we will follow the workflow that I present before, and you will see that with that we can arrive to have a good neural network to describe the a high-dimensional system like this. So briefly, I will speak about the motivation of this work. The motivation was a very nice experiment that was made by Kurahashi and collaborator in Japan in 2019. In fact, Kurahashi was able to control the initial orientation of OCM molecule before it impact with graphite surface. The experiment is able to do that. And after the study that he made, he obtained that for sure there is a correlation between the angular scattering distribution with the initial orientation of the molecules. So in the first step, what we want is to understand what happened. And for that, by the theoretical point of view, what we made was a theoretical study using vast calculation. So we perform IMD calculation. We perform 200 trajectory per geometry with 4 picoseconds of molecular dynamic calculation, was a spin polarized calculation, and we use the PBE functional with the correction of van der Waals. So after this very expensive calculation, I must say, we obtained that the general trend of experimental observation has been captured by the IMD simulation, but in any case, there is a statistical limitation due to the computational cost of the IMD calculation. So as you know, there is a limitation for the computational cost, so you can perform only limited number of trajectory, and then your distribution, you must to use beams that are more big than what you want. So there is some problem in the statistics, and for this reason, our goal with this neural network PES was to obtain and validate this neural network PES to perform molecular dynamics study on the same system. The question here is why to obtain neural network PES? Well, the answer is to get the accuracy of the first principle method with the efficiency of the force fields. As you know, the computational cost using the neural network PES is much lower than the DFT-based calculation. Also, the flexibility of the neural network algorithm allows to obtain a full dimensional PES. So we take into account all the degrees of freedom of the system, and the surface atoms are free to move. This point that is very important, that we will reuse all the data that we obtain of our very expensive IMD calculation. We are available already more than 2 million of DFT points. What is very nice in the IMD calculation to use in the construction of the neural network is that the configuration space is very well explored, because in fact, already you make a molecular dynamics calculation. So all the configuration space that are important in the scatter process is already explored, and you will use this data to build or to obtain a neural network PES. So, as I mentioned before, I begin with the workflow I showed before. So here we have in the step of the sampling of the configuration. As I said before, we have around 2 million of DFT points, but we need to reduce that to 10,000 because we cannot make the training of our neural network with the 2 million of points. So we need to reduce that, and for this, for that, we need to have efficient sampling. So for that, what we did is to divide the configuration space in 3 different regions. The first region that I named weak interaction region is a region where we don't have a lot of interaction. The configuration are very similar, and you don't need many points in this region. So for this reason, we take around 20% of our configuration for this region. The second region, that is the strong interaction region, is very important to sample well, because here we have all the interaction. We have the interaction with the surface and the absorption, and we have a wide variety of configuration. So from this region, we take around 40% of our configuration. And the region 3 that we call medium interaction is very important also to sample well, because it's the analysis region. And we have a wide variety of the configuration. Here we have all the configuration that depend on the molecular orientation. And also we have the vibration and the rotation that can happen after the collision with the graphite surface. So with that, we obtain a sampling of 10,000, training set of 10,000 configuration. And we also take 20,000 configuration, and we reserve that for the validation set. Okay, so this is the first step. Unfortunately, it's not enough take configuration from the IMD calculation. And this, we know that because we made some tests, and we saw that with the neural network obtaining only using the IMD configuration, we can have some problem to describe well the barrier of the system. For this reason, what we did was to add the dissociation curve of the O2 at different distance from the surface. With that, we obtain a better description of the dissociation barrier and molecular vibration. And also, we add approximation curve of the O2 our different surface seat, and with that, what we obtain is accurate description of absorption wells. So we add to the original training set 10,000 new configuration. So at the end, what we have is 20,000 configuration with the corresponding energy. And we use for the training process, for the training of the neural network, the Atomic Energy Network open source software that is available in this address. We use for how, like Symmetry Function, the Chebyshev descriptor is a symmetry function that are included in ANet software, but are very similar to the Veles symmetry function. The architecture of the neural network that we used was 2 hidden layers with 30 nodes each one, and the optimization algorithm is the BFGS algorithm. So here I show the result of the training process in the left figure. What I show is the evolution of the error during the training process. As you can see here, we have the 90% of the configuration of the 20,000 configuration. We use the 90% for the training set, and we use 10% for the test set. So in the training process, we use the 19%, and we see that we have decrease in the error during the iteration. In this process, you need to be very careful to don't observe this curve. In fact, we don't observe the curve. I put here to say to you that you need to be careful. Don't have overfitting in your training process. How do you detect the overfitting? Well, when the test set begin to have an increasing in the error during the training, while the training set continue with the decrease of the error. So after our training, the training of our neural network, we obtain a very good average error of 0.2 millitron volt per atom. And if you observe here the correlation between the neural network energy and the DFT energy, the correlation is perfect, and the training process is well done. So now we pass to the validation of the neural network potential energy surface, and for this we use 20,000 DFT configuration that is important. That is were not used to train the neural network. So here I show in the left figure the correlation between the neural network energy and the DFT energy. Here the correlation is very good. One more time, we have a very good correlation here. I represent the total error and not the error by atom. So this is the total error of the neural network was in average 70 millitron volt. That is a very, very good result. And if we see in the right figure the distribution of this error, we can see that around the 90% of the error are below 25 millitron volt. That is a very good result in the energy for the energy in the case of the neural network. So in this step, we can say that the neural network can predict very well the energy of the system. Also, you need to check if the force are well predicted, and for this reason, we select one atom of the oxygen molecule and one atom in the surface, in the topmost layer. So here I represent the correlation between the force calculated by the neural network and the force calculated by DFT. And we can see that here the correlation is correct. We have an average error around 0.2 electron volt per angstrom. That is a very good result. If we see in detail the distribution of this error, we can see, that the 90% of the error are below 0.25 electron volt per angstrom. Also, we check the duration of the force, and for this, here I represent the distribution of the error. We can see here that the 90% of the duration of the neural network force compared with the DFT force are below 10 degrees of deviation. That is also a very good result. So this neural network is able to describe well the energy and the force of this high-dimensional system. We may also MD validation using molecular dynamic simulation. And for that, what we did was use the same initial condition that we use in IMD calculation. So we perform only 200 trajectory at the same surface configuration with the same temperature, and we obtain the same scattering probability and an excellent agreement in angular distribution. And for that, we can conclude in this point that the neural network PES that we obtain is able to describe accurately the interaction between O2 and the graphite surface. So here I show the comparison in the use of IMD method and the neural network PES. For sure, we take into account all the degrees of freedom, but with the neural network PES, we can make 60,000 trajectory comparing with only 1,200 with the—
Alejandro, 5 minutes left. 5 minutes.
Yes, thank you. So, and the most important thing here is the time that you need for make one trajectory using IMD. For this system, you need 48 hours to make one trajectory. And with using the neural network PES, you only need 4 minutes. So we use a homemade Fortran code that is able to use the neural network obtained by INET. We have 38 atoms free to move, and we obtain much better statistics with a much lower computational cost, 50 times number of trajectory comparing with the IMD calculation, and we have a 700 faster computer. We are 700 faster computing a single point energy and force. I want to say that I use for my calculation 24 CPU and 24 GB of RAM. So with this neural network, for sure, we perform massive MD calculation and we obtain very good results. We obtain a small angular distribution that allow us to have accurate comparison with experimental results. We have the opportunity to obtain insight in the reaction mechanisms using the energy transfer that they happen in the scatter processes. And also with this statistic, we are able to report the raw vibrational distribution of the scattered molecule after the collision with the graphite surface. So for the conclusion of my talk, I want to say that the use of the neural network PES to study high-dimensional system allows to get the accuracy of the first principle method with the efficiency of the force fields. This is very important that using that, we reuse the data from IMD calculation. The neural network are very flexible algorithms to obtain full-dimensional PES. It's a method that is applicable to a wide range of systems. The molecular dynamics can be performed with lower computational costs, allowing a robust statistical description of the processes. In any case, I want to say that obtaining and use a neural network PES is a complex process and have its own limitation. This is very complex, the selection of the data sets. The data set, also the selection of the symmetry function you can use, but you need to know you have some option, the validation and the retraining, and also the computational cost is not more than one day. You must pass a lot of days to have a good neural network and to have a good quality for your calculation. I want to say also that the neural network that you obtain mimics the IMD calculation, because it's linked the quality to the DFT calculation accuracy. The number of different species here is limited. The complexity of the calculation increase with the different species that you add to your system. And of course, it's specific for the study process that you want to simulate. So at the end, the combination between IMD and the neural network PES is the best option. Well, I think that yes, for the moment. Thank you very much for your attention. I am ready for your question.
Smashy.
Yeah, thank you. I have two questions. The first one is technical one. You're establishing an scheme. So in this transfer, can we transfer to other system? Let's say if we would like to study N2 with graphene, can I use an N or should I do the work from zero?
Yeah.
And So the second question is to go to reality. Okay, there is holes in the graphenes when you synthesize that.
Yeah.
So should you can you adapt your potential, or should you do the work from zero again to go to the reality or not? These questions. Thank you.
Yeah, but well, very interesting question. Thank you very much. In fact, if you want to use the neural network to study the scattering of N2, for example, from the graphite surface, you need to obtain a new neural network. This neural network is adapted to the O2 graphite system. In any case, all the work that you make with the training of this neural network, maybe you can use a little of this work for training a new neural network using new configuration, but now with the information of the scattering of N2 over graphite. This you can use maybe, and you can economize, or you can have the result maybe faster. But in the neural network, and this is important, that you obtain for a specific system, you can only use for this system. In the case of the hole in the graphite surface, yes, I think that this neural network can be adapted to this kind of system, but in any case, we need to add some configuration with this information to the training of my neural network in order to describe well a system of a scatter of O2, but in graphite, not totally cleaning, so with some hole inside for some defects. Yeah.
More questions?
Yes, Alejandro, the last slide you showed, and you, I didn't get what was experiment and what was calculation.
Yeah, in fact, in this slide, I showed the angular distribution, but the problem is that the comparison, the problem is that the comparison with the experiment is a little complex, because the experiment have a fixed detection geometry. So the experiment, you select in the experiment one incidence angle, and you can only detect the molecules that are scattered in an angle that incidence angle plus the detection angle must to be 45 degrees. So in fact, as you can see in this slide, you have this point, this line with point, and this is, for example, the detection of the experimental in the experimental results. So you select, for example, 22.5 degree of the incidence angle, and you can detect at 22.5 degree only. So to compare our results with the experiment results, we need to stay here, and we need to take the intensity of the different orientation. And when we make that, we obtain exactly, well, not exactly, but we obtain a very good agreement with the experiment of Kurahachi. So what Kurahachi did, I will come back to what Kurahachi did was, for example, we perform our simulation at 22.5 degree, so that in the experiment of Kurahachi, to compare our result, we need to stay here in this region only. So it's a little complex to explain the agreement with the experimental results, but because in fact, in the experiment, you cannot obtain the full angular distribution. You can only obtain the value of the intensity of the detection of a scatter molecule in one angle. And after you make this for different angle. In this case, we made the simulation only for 22.5 incidence angle.
Okay, thank you.
I don't know if it's clear, but I cannot show the same view for the experimental results, because they don't obtain this kind of results.
And I wondered also, so you said you did millions of DFT calculation to train your neural network. And in fact, if you take into account the time you spend to train your neural network, is it still faster use it than.
For be clear, we have available 2 million of points because we made IMD calculation and we have all these points available. But for the training process, we need to reduce this number of points. We cannot perform the training process using the 2 millions. So for this reason, we reduce and we made a sampling configuration. So we use around 20,000 configuration at the end. And I seen that here, I say I put the time that you need to train a neural network using 20,000 configuration, using 24 cores and 24 GB of RAM in your calculation. You need around 1 month of calculation to obtain a neural network PES.
Okay, thank you.
And this is in the best of the case. In any case, I want to say that this is the last neural network that I obtained that works well. But before this neural network, I obtained 30 neural network before. I made all these tests. Really, yeah, well, I think that the time that you need, taking into account the time for IMD calculation, plus the time for obtention of the neural network PES, I think that you need around 1 year of work.
Okay, thank you, Alejandro. Let's thank Alejandro one more time. And we will go for the third talk of this afternoon. Amendra Pandey. Amendra, can you come to set up your computer?